Namaskaram. Welcome to another session of multiple integration. In this session, we will define triple integration and evaluate some problems. Already, we learned the concept of double integration, and this is the actual definition of double integration, and we denote this limit by this double integral notation. Okay, in this session, we will extend this concept for a three variable function, and we define the triple integral. And what is the analogous extension of this definition for a three variable function? Okay, in the case of one dimensional integration, we integrate over an interval AB. Okay, and in the case of double integral, we integrate over a region. Region means it's a subset of R2, a two-dimensional plane. So what is the analogous extension of triple integral? We integrate over what? We integrate over a solid in 3D. Okay. Okay, that means we are going to define a concept like this: a triple integral over a solid. Suppose we consider this green solid. Suppose we consider a solid like this. So we are going to define triple integral over G f of x, y, z dv. Okay, then how to define this triple integral analogous to our double integral and one dimensional integration? Okay, in our two-dimensional integration, that means in double integration, what is the procedure? We subdivide the region into small rectangle. Okay, instead of small rectangle, here we divide the solid G into small cuboids. Okay, so first we divide the solid G into cuboids by planes parallel to the coordinate planes. As similar to two-dimensional integration, here we assume that there are n such cuboids completely lying inside G. Okay, we discard those cuboids that which contains the points outside G. Okay. Okay, next step is choose an arbitrary point from n such cuboids. Okay, suppose this is our kth cuboid. Then we choose an arbitrary point xk star, yk star, zk star. Clear. And also we assume that the volume of this cuboid, kth cuboid, is delta vk. Okay, in two-dimensional integration, we assume that delta ak, that is the area of the kth rectangular piece. Here instead of rectangle, it's a cuboid. So we take delta vk as the volume of the kth cuboid. Okay, in the case of two-dimensional integration, we consider f of xk star yk star into delta ak. Okay, then you take that sum, k is equal to 1 to n. Instead of f of xk yk, here we consider the f of xk star yk star results k star into delta vk. Okay, then you take the sum. This extension is similar to our two-dimension. Okay, in the case of two-dimension, we have a geometrical interpretation. Here now we have no geometrical interpretation. We just consider everything analogous to two-dimension. That's all. Okay, so we consider k equal to 1 to n f of xk star yk star zk star into delta vk. And again, what is the next step? In next step, we consider the limit n tends to infinity, and we denote this limit by double integral over r f of xy dA. Okay, so next step we consider the limit n tends to infinity. And what is the analogous representation of this limit in terms of integration? Yes, this is triple integral over the solid G. Okay, we divide the solid. Here we divide the region R. Okay, so triple integral over G f of x, y, z dv. So we define an infinite sum like this: limit n tends to infinity, sigma k is equal to 1 to n f of x k star y k star z k star into delta vk, and we denote this infinite sum as triple integral over G f of x, y, z d. Okay, so this is the formal definition of triple integral over a solid G for a three variable function. Okay, as similar to two variable function, we know the infinite limit is not easy to calculate. It's almost impossible. Okay, so how to evaluate such triple integration? So let's see one simple case. As similar to two variable function, two variable integration, here we consider a rectangular box like this. Okay, so if G is a rectangular box, then you can easily evaluate the triple integral using the iterated integrals. Okay, in the case of two-dimensional integration, we consider a rectangular regions and non-rectangular regions. Here we first consider one simple case, that is a rectangular box. So a rectangular box means x is bounded by a and b, y is bounded by c and d, and z is bounded by some g and f. They are all numbers, a, b, c, d, g, h, all are numbers. Then we can evaluate triple integral over that solid g over the rectangular box g using this iterative integration. You first integrate, I think all of you familiar with this integration, because first you integrate with respect to z, then we substitute the limits, then you integrate with respect to y, then with respect to x. Okay. And one more thing here, actually order of integrations does not matter because all the limits are numbers. So either you can integrate another order, maybe like this, a to b, g to h, integral c to d, f of x, y, z. Only difference is the order of integration is different because c to d is corresponding to dy. So you can integrate dy. This is for dz, so dx. So you should integrate in this order, that's all. Okay. So that's why order of integration does not matter. Whatever be the order, you just interchange the limits and this derivative terms. That's all. Okay, consider a problem. Evaluate the triple integral over g 12xy square z cube dv over the rectangular box g defined by the inequalities -1 less than or equal to x less than or equal to 2, 0 less than or equal to y less than or equal to 3, and 0 less than or equal to z less than or equal to 2. So first you have to set up this integration in terms of iterative integrations. So this is equal to integral range of x, range of y, and range of z, 12xy square z cube. The order of integration is dz, dy, dx. So first you have to integrate with respect to z. So this term becomes z raised to 4 by 4. You can cancel 1 4 from this 12. So this becomes 3xy square z raised to 4, 0 to 2. Next you substitute 2 and 0 for z. So this becomes 2 raised to 4 when z equals 0, term is 0. 2 raised to 4 is 16, 16 to 3 that is 48. So integral becomes like this. Next you have to integrate with respect to y. Okay, so this becomes -1 to 2, 48x, y square becomes y cube by 3, 0 to 3. Next you have to substitute 3 and 0. When y equal to 3, this becomes 3 cube by 3, that is 3 square, that is 9 into 48. When y equal to 0, term is 0. So this integral becomes, so integral -1 to 2, 432 x dx. Okay, next you have to integrate with respect to x. So this is x square by 2. Okay, so we can cancel 1 2. So this is 216 x square. We substitute upper limit and lower limit and simplify. So this becomes 648. So this is the final answer. Okay. Okay, next we are going to integrate over a more general region. That means a solid like this. So here the solid is bounded below by a surface, that is z is equal to g1 of xy, and bounded above by also a surface, that is z is equal to g2 of xy. Okay, and laterally by some other region. Suppose we consider a solid above this region R. Okay, and bounded below and above by surfaces. So we have a solid like this. So next we have to integrate our solid like this. Okay, how to integrate over such solids? Okay, so we have to compute this integral. So idea of integration is almost similar to our double integration. Our aim is to cover this solid by changing x, y, and z. Okay, so it is clear that what is the range of z? Z value, suppose you think about a strip, a vertical strip like this. You think about a vertical strip like this. We have to cover this entire solid G by moving the strip. Okay, so what is the lower value of the strip? Lower value is always from the surface. That means g1 of xy, right? And what is the upper value of z? That is g2 of xy. Then we have to cover the solid. To cover the solid, xy should moving along this region R. Clear? So xy should moving along the surface, along this region R. Then automatically this strip is moving along the solid. So that's the idea. So suppose this region, we denote this region. Here this region is nothing, it is a projection of the solid in xy plane. Okay, that is our R. So we can convert this double integral as f dz dA over R. So we can convert this is like this, double integral over R, because to cover this entire region, double integral over R, integral g1 to g2 f dz dA. Okay, then you can use any rule for double integration, because now this is in terms of double integration. You can compute this double integration using any previous rules for double integration. Either you can compute this is in Cartesian or in polar coordinates. Okay. Okay, that is another result. If G is a solid, solid with upper surface is like this and lower surface is G1 of xy, and R is the projection of G onto xy plane, then we can evaluate this triple integral using this formula. Okay. Okay, consider another problem. Let G be the wedge in the first octant that is cut from the cylindrical solid y square plus z square less than or equal to 1 by the plane y equal to x and x equal to 0. Evaluate this triple integral over G is at dv. Okay, so first we have to identify the region G. Okay, consider, okay, what is x equal to 0? X equal to 0, we know that x equal to 0 means this yz plane, so this plane. Okay, the yz plane is x equal to 0. And what about this one? Y square plus z square is less than or equal to 1. And what is y square plus z square equal to 1 in a plane in 2D? In 2D, we know that y square plus z square equal to 1 is a circle in yz plane. Suppose in this is our yz plane. In yz plane, this is a circle with radius 1. Then actually, what is the x value? Here x value equal to 0. Because in this equation there is no restriction for x. So you can draw the same circle at x equal to 1. Suppose this is x equal, sorry, x, suppose you can say x equal to 3. Then we can draw a circle at x equal to 3. Right. Similarly, you can draw the circle at x equal to minus 5. Suppose this is minus 5. Clear? So what is the totality of all such circles? The totality of all such circles form a cylinder. That's why this is called a cylinder. And this is, of course, this is less than or equal to 1. So it contains interior points also. So the solid of cylinder. Okay. That's why this is a cylinder. This is the equation of cylindrical solid. Next we have to cut this cylinder using, okay, we consider only the first octant. This is positive x-axis, this is positive y-axis, this is positive z-axis. So we consider only the first octant, the portion of the first octant. Then what about y is equal to x? We know that y is equal to x is the straight line like this. Okay, this is y is equal to x in xy plane. But there is no restriction, in for z. So you can draw the straight lines in for any z. Suppose x z equal to 4, then you can draw a straight line like this. So what is the totality of all such straight lines that form a plane passing through y is equal to x? Clear? Vertical plane passing through y is equal to x. So we have a cylindrical solid like this. Next we have a plane like this, and one more plane x equal to 0. That is this plane. Okay, so a solid above almost like a triangle. Okay, this is a, okay, and this we have to find this intersection. What is the intersection of this cylinder with the xy plane? To identify this boundary, we have to take the intersection of cylinder y square plus z square equal to 1, that is a boundary, together with the xy plane, right? Xy plane means z equal to 0. So if you substitute z equal to 0, this become y square equal to 1. So y is equal to plus or minus 1. So equation of the straight line is, this straight line is y is equal to 1, and we have one more straight line on xy plane at this end, that is y is equal to minus 1. So of course this intersection is a straight line. What is this straight line? This line segment is a part of the straight line y is equal to 1. Okay, so we can redraw the base. So actually its base is almost like this, like a triangular region, and this is y is equal to 1. Okay, and this, what is the equation of this portion? That is y is equal to x. Okay, then you can easily integrate. So this is the almost shape of the region. I will show the exact shape. Okay, this is the shape of that solid. We have a cylinder in this x direction, and we cut using a plane y. This equation is y is equal to x. We cut using a y is equal to x, and we have one more plane, that is x equal to 0. That means y is at planes. So the solid bounded by these three equations is this solid. So we have to integrate over the solid, and we know that the equation of this straight line, this portion is y is equal to x. Okay, and what about this one? This is y is equal to 1. Okay, so we can draw. So next we have to set up this triple integration. So what about our triple integral? Triple integral over G. Okay, this is our triple integral. So we consider this triple integral, and this is equal to double integral over R. The projection, that is our R, is a triangular region, into integral. What is the lower value? You consider a vertical strip like this. You consider a vertical strip like this. Then what is the lower value of Z? Z is 0. What is the upper value of Z? Upper value of Z from this equation. Which equation? Y square plus Z square equal to 1. And from this equation, you can easily solve for Z. One more thing, in the first octant, it is clear that Z is positive. So that's why Z is equal to square root of 1 minus Y square. So square root of 1 minus Y square. So this is the range of Z. And to cover the solid, we have to move this strip along this region R. That's why double integral over R. Okay. And Z, dz, dv. Not dv, dA. Okay, this is for double integration. Okay, next you have to set up this double integral. How to set up? You consider the region R. You just redraw the region like this. We consider positive y axis in this direction and positive x axis in this direction. Then this triangular region is like this. Okay, and it is clear that here y is varying from this point to this point. The lower value of y equal to 0, upper value of y is equal to x. And to cover the region, oh sorry, this is the direction of x, right? This is the direction of x. So here the lower value of x is 0, and what is the upper value of x? That is from this equation, that is x equal to y. To cover this triangular region, what is the range of y? Y should vary from 0 to this point. So y should vary from 0 to 1. Okay, that's why we redraw the triangular region like this. And we consider the strip like this, horizontal strip. So x equal to 0 to x equal to y, and y equal to 0 to y equal to 1. So now you can easily set up the double integral. So this become 0 to y, 0 to 1. And this 0 to y is the range of x. So order of integration is dx dy. So this is the iterative integral corresponding to this triple integral. Okay. Okay, now it is only the matter of integration. First you integrate with respect to z. So this becomes z square by 2, 0 to 1 minus y square. Okay, 1 by 2 is common, you can take outside, it's a constant. So this become square root of 1 minus y square. So this become 1 minus y square dx dy. Next you have to integrate with respect to x. So it is clear that with respect to x, this 1 minus y square as a constant. So what is the integral value? 1 minus x square into x. So this become integral 0 to 1 minus y square into x, 0 to y dy. Okay, next you substitute upper limit and lower limit for x. So 1 by 2, 0 to 1 minus y square into y dy. When x equal to 0, the term is 0. So you can expand this one. So this become y minus y cube. So this become 1 by 2, y square by 2 minus y raised to 4 by 4, 0 to 1. Next you can substitute upper limit and lower limit. When y equal to 0, whole term equal to 0. So when y equal to 1, this become 1 by 2, 1 by 2 minus 1 by 4. Upon simplification, this become 1 by 8. Okay. Yes, final answer is 1 by 8. So this is your homework. Okay, thank you.